Log on, tune in, find out. Another good idea from Cambridge.
University of Vienna, talking about diffusive quantum models. Okay, yeah, thank you very much. Thank you for the invitation to Eugene and Peter Markovic to come back to Cambridge. Okay, yeah, I will speak about something which is quite different from the previous talks, since this is okay, thank you. Now it's working. Yeah, once again, thanks to Peter and Phi for invitation, for coming back. I will speak about something which is slightly different compared to the two talks in this morning. Since I will speak about the mathematical analysis of certain classes of quantum fluid models, PDE models. And in fact, these models, they include some diffusion, some dissipation, motivated by several facts. So one idea is that even in Bose-Einstein condensates, you may have, or some people from physics found the onset of dissipative phenomena. So these models try to understand better how dissipation happens in quantum models. And I will speak about three types of models, quantum diffusion models, so-called of fourth order, including a fourth order differential operator, or even a sixth order differential operator. And then the third model is the quantum Navier-Stokes model. So this can be motivated, one motivation is maybe more from the physics point of view. So here's a graphics for the so-called feature size, which is essentially the length of the transistors in a processor. So here are the numbers from Intel. And you see that it started about in the 70s, where processors have been produced. There the single devices have been quite large, so more than, here you see 1000 nanometers. And nowadays it has reached a very, very small size. So on that computer, which is here on the table, it's about 45 nanometers. And the next year it's expected to go down even to 22 nanometers or 32, depends a bit on the technology. So in these small sizes, you will have quantum effects, which you already have in bigger devices since more or less the year 2000, but they're treated more as a correction factor or even as something which is disturbing in the devices, in industrial needs. However, when you have such small length, then the quantum effects have to be modeled much more accurately to understand better what is happening. And using Schrödinger equation or other approaches, Wigner equation, this is typically numerically quite expensive. And for industrial needs, for instance, at the company Infineon, we have some collaboration with them. They want to have quite simple model in order to have some idea what happens when they want to produce these devices, and the fine-tuning is made by the people doing the experiments. Therefore, it could be interesting to use fluid type models, since they are well understood from a numerical point of view. They're numerically rather cheap, and we are trying to include some quantum effects, hoping that still the numerical solution is not so difficult. In fact, the solution should be cheap for industrial needs, maybe even less accurate than when using a Schrödinger model. So this is the motivation more from the, let's say, application point of view. However, I will more be on the mathematical side and give a motivation more from a point of view of mathematical analysis. And the motivation is that these models, they have a very rich mathematical structure. They're interesting. They are very difficult, so I present to you these models here on the slides. I will give you details later. This is the fourth order model, the sixth order model, and the quantum Navier-Stokes model. So the fourth order model is an evolution equation for the particle density, electron density n, Here you have the time derivative, divergence, gradients, Laplacian. You see you have a fourth order differential operator, highly nonlinear. Looks very difficult. Even more difficult is the operator of sixth order. And in the Navier-Stokes model, it looks a bit like the Navier-Stokes equations, where you have a quantum correction and the viscosity on the right-hand side, also highly nonlinear, coupled. And it's not clear at all how to solve these models, how to understand them mathematically. And the aim of my talk is to convince you that there's a lot of structure in it, and you can develop nice mathematical theories, also usable for other fields where you have higher order equations. Okay, let's start a bit where these models are coming from. And this slide is a very simplifying picture just to give you some expression. In fact, this quantum fluid modeling is well known since the beginning of quantum mechanics, since the works of Madelung in 1927. And starting with a single-state Schrödinger equation, when you decompose the wave function psi, so here the Schrödinger equation, in the amplitude, square root of n, and the phase function s, epsilon here is the scaled Planck constant, v is some given potential, then you will get the so-called Madelung equations, which is the mass conservation equation here for the particle density n and the current density j, which is defined in that way, and balance equation for the momentum or the current density, which is given here, which looks very much like the Euler equations of gas dynamics. Since you have a convection part, here you have a force part due to the electric field, but you have here a correction term, which is the quantum correction, and which involves here between the brackets second order differential operator, which can be seen as a so-called Bohm potential. Okay, there's something missing. There's no pressure here, and this is natural since it's just a single state approach. So if you want to include some pressure, one approach could be, for instance, using the approach of Peter Markovich and Ingo Gasser, which are both here, to use a mixed state Schrödinger equation, and then you can get, using an appropriate closure condition, a pressure term here. I'm just using this pressure here given by n, so the isothermal case. And then you get something which is even closer to the Euler equations. Okay, you can simplify these equations, which are of third order, by using a diffusion scaling. That means that you are considering the low current density and a large time scale. Then you get a tau square here. I should add that here I have added a relaxation time approach. So I include some dissipation on the right-hand side, an ad hoc approach, using the relaxation time tau. And here, since I have a j square, I get the tau square here in front. Now, if I pass to the formal relaxation time limit, that means I study the equation in the regime where the relaxation time is small, then these two terms here cancel. Oops, sorry, these two terms here cancel. And what you get is an explicit expression for the current density, which you can plug in the mass conservation equation. And what you get is, in fact, what you can call a quantum diffusion equation, which is of fourth order. Yeah. Okay, so this is a very simplifying picture. I will give you some hints how you can derive these models from a maybe more physical point of view by going to the first model class, the quantum diffusion models of fourth order. Okay, so this here is again the equation with the differential operator. You see that I've neglected all the other terms, the force term, the pressure, and so on. And so this is the most difficult part. If you have understood this one, then you can add the lower order terms. There's no problem in the analysis. Okay, so this is an interesting equation, since in fact I found this equation in a one-dimensional version in a completely different context. I found it in a paper by Derrida, Lebowitz, Speer, and Spohn, who modeled a spin system. And more precisely, they here the variable is the scaling limit of a probability density, which measures the deviation of the spin system where you have spin up and spin down. So in between this interface, it's a kind of two model. And what they got is exactly this kind of equation here in the one-dimensional context. And And you can derive this also in a second way when you're using the Wigner BGK model. So that means you already know what is a Boltzmann BGK model from the previous talk. The Wigner equation is just, let's say, the quantum version of the, if you like, Vlasov equation. You are putting on the right-hand side a BGK collision operator, and you can derive these quantum models by using a Chapman-Enskog expansion. And this has been done by Pierre de Grand, Florian Mihatz, who is also here, and Christian Rinkhofer a couple of years ago. Okay, so now let's turn to the mathematical analysis. So we want to prove existence of solutions and their qualitative properties. So how can we do? There are two difficulties, main difficulties. First of all, I would expect from the physical derivation that the particle density should be positive, or at least non-negative. But the problem is, with a fourth order differential operator, there's no maximum principle in general. So how can I do this? How can I prove it? And I need this proof, since otherwise I could not define the square root and not the quotient. So this is the first problem. The second problem is, due to the highly nonlinear structure, it's not clear at all how to get a priori estimates. But without a priori estimates, you cannot expect to get global existence of solutions. So there's another problem due to the nonlinearity. So due to these problems, the first result, which was given by Blair, I think Leibowitz and Speer in 94, they only achieved local in time existence of solutions for the 1D model, since the one space dimension was just the model where they have derived it from the physics. And the local in time existence, they proved it by using some semigroup theory, but due to the lack of a priori estimates, they couldn't continue the solution. Then with René Pinau, we could improve the result in the sense that we can get global in time existence, but only for weak solutions, whereas for the semigroup theory, they could get the existence of classical solutions. But nevertheless, was for a couple of years not clear how to pass from 1 dimension to 3 dimensions. And the reason is that in the 1-dimensional case, there's a very special kind of Lyapunov functional, which gives us some a priori estimates. And this kind of functional is not available in higher space dimensions. And only 2 years ago, independently, Giannassa Savary and Toscani from Italy, and with Daniel Mattes from Munich, independently we got the existence of solutions in the multidimensional case. Okay, how did we do that? Or first maybe the result. So in fact the critical quantity is the entropy, the physical or logarithmic entropy here, defined by E1. And we are looking for the equation only on the torus with periodic boundary conditions. I will explain to you later why we are doing so. We just want to avoid boundary integrals when integrating by parts. And the nice result is what we get is, so when you have an initial datum which has finite entropy up to 3 space dimensions, then we can get a weak solution which is non-negative in these kind of Sobolev spaces. So we have regularity only for the square root in H2. And we also get exponential convergence to constant steady state. The steady state is constant since we are working on the torus. The nice feature is that we can compute the decay rate explicitly, or at least get some information on that. Moreover, this problem has some 2 surprising properties, since we get non-uniqueness for the evolution problem in a space which is slightly larger than the space of weak solutions, which is here L2. When you go to L1, then you get non-uniqueness. So this is somehow surprising, and which comes from the fact that you have a lot of steady-state solutions, possible explicit solutions, and they are not entropy dissipating. Yep.
In Wasserstein space,
Mm-hmm.
there's uniqueness.
Yep. Mm-hmm.
So how does that?
This space here is slightly larger.
Well, it's different space. I would say.
It's a different space. Yep. Yep. Mm-hmm. Mm-hmm. Mm-hmm.
Measures don't stay in this space.
Mm-hmm. Mm-hmm. But so the reason for the non-uniqueness is that we have one solution which we get here from the existence analysis, which in fact is maybe closely related in some sense to this Wasserstein approach. And then we have a second solution, which is an explicit solution, steady state solution, which touches 0, but still is in that space. So it's
And there's infinite Wasserstein distance to the first solution.
I would guess, but I would need to compute.
Not, there's a problem.
Yeah, right. And in fact, the second solution here, I wrote it here in the last line, it's a solution which touches 0. So in general, you will not have positivity of solutions, except maybe, but we don't know, when you start with the positive solution. So how did we prove that? So there are two ideas in order to overcome these difficulties. So the first thing is, how can we prove the positivity of solutions? And in fact, the idea is a kind of reformulation of the equation. So it turns out that this equation can be written in that way, where y here is given by this relation. So it's just, we have a kind of exponential transformation of variables. So the nice feature is that this is also a symmetric operator, and this enables us to use these standard tools of Lax-Milgram lemma and so on. And moreover, if y has some regularity, then the density is strictly positive just by definition, by the exponential. So this is the first idea. The second idea is how to get the a priori estimates. Okay, let's do the standard thing that we multiply the equation by the logarithm of n, since then we get some information about the physical entropy, and you expect from physics that this quantity should be bounded or maybe even non-increasing in time. So you do the same here on the right hand side, then you integrate by parts, the divergence is put on the other side. Now I'm using that I'm working with periodic boundary conditions, I do not have boundary integrals. Then I get the gradient n over n, it cancels with that n here. I integrate by parts a second time, this one here on the other side, and then I get the gradient, the Laplacian in here. Okay, and then the goal would be to see if this has a sign, but this is not clear at all, since you have the Laplacian of the square root and the Laplacian of n. So you would need, or you need to integrate by parts even several times more in order to see if this is non-negative. But this is a hard time. So if you do so, then you need a long weekend to understand this. Or another way is what we tried to do is a kind of systematic integration by parts. And now I will explain to you what do we mean by a systematic integration by parts. And the idea is very simple. In order to make the talk not too technical, I will just consider here the one-dimensional situation, since then it's easier to explain how we did it. And what we want to prove is that this quantity here, which is just the one-dimensional version which was on the previous slide, minus that one here, so this is just the right homogeneity, has a sign. Okay, so this is the goal. Okay, how can you do integration by parts? Written in a more formal way, you can say integration by parts is just an integral, that one here for instance, where this x, for instance, is put here on the other side, then you get an nx to the fourth, but I write everything on one side, and then it's clear that this one should be a derivative of something which vanishes since I'm working on the torus with periodic boundary conditions. So how many integration by parts do they exist? In fact, there are just two which are useful here, I1 and I2, and both integrals are 0. So I could say that this quantity here, from which I would like to show that this is non-negative, can be written as the sum, as a linear combination of this integral I1 and I2. In fact, this is completely trivial, since I1 and I2, they're 0. So here, up to now, I have nothing done which is of interest. I need a new idea. And the new idea is that I identify the derivatives with polynomial variables. So then I can write everything as polynomials, and I'm doing so. In fact, this quantity where I want to prove a sign, I write it as this polynomial SC, which is given here. In C, I should mention this, maybe I go back, is just some constant, and I want to find that constant. And as possible, an explicit expression for C. Okay, so the C here appears again, and then these two integration by parts formulas can be translated into these polynomials here, T1 and T2. And then the goal is to show that if I can prove that there exists a constant C and C1 and C2, such that for all arguments this polynomial has a sign, then it means that the integrand has a sign, and also the integrals. That means that this here has a sign. Okay. The nice feature now is that up to now I've just transformed the problem to another problem. But I'm claiming that this problem is in some sense, let's say, more accessible, not easier, but more accessible, since it's well known. It's well known in real algebraic geometry. It's called the decision problem, which you can solve by quantifier elimination, and there's even software for doing so. And in fact, it's an old problem, so Tarski already in 1930 proved that this quantified statement can be reduced to quantifier statement, maybe giving conditions on the constants, in an algorithmic way. And this algorithm has been implemented, so for instance, in the software Mathematica, for simple problems, for more difficult problems in the software QuadCAD, which is an acronym for quantifier elimination by partial cylindrical algebraic decomposition, so this method from real algebraic geometry. And the advantage is that this gives a complete and exact answer, it gives a proof. You just have to translate somehow what's coming out of the computer in the mathematical terms. And as always, when there are too many advantages, you're looking for a drawback, and there's a big drawback, since the algorithms, they are, at least up to now, doubly exponential in the number of variables and coefficients. So that means for simple problems, you can solve it easily by using the computer. For big problems, and big problems is very easily reached for a couple of variables and a couple of coefficients, then it's out of reach with modern computers. So you have to do it by hand, and you have to use the brain. But that's nice, since we don't get jobless. Okay, in fact, for the multidimensional model, this is far too difficult for solving by the computer. So we want to prove, in the multidimensional case, that this here minus some kappa times this object here has a sign. And in fact, the idea, and here I only give the key ideas, is to write down not all possible integration by parts, and by writing this as partial derivatives, you could do so in principle. That before I did it in one space dimension, but now you just have more partial integrations, each for the single variables. But this gives a huge number of variables and integration by parts formulas. So it makes more sense to look for scalar variables like the gradient square or the Laplacian, and working with these variables to reduce the complexity of the problem. Then you have still a lot of integration by parts formulas, which we call shift polynomials, the corresponding polynomials. For instance, those where you compare the Hessian matrix with the Laplacian. Since this is in one space dimension is the same, but in multi-dimension it's different. And it turns out that there's a special formula which is very useful to translate between these two objects. And then what we achieved is that we can solve this quantifier elimination problem by hand. Yeah? So giving a rigorous proof. Okay, that means we can really prove this inequality here, written down again. And then we know not only that the logarithmic entropy is a Lyapunov functional, but we also know what we're calling typically entropy. That means that we have a kind of entropy dissipation, which gives us information on the essentially on the H2 bound for the square root of n. Okay. Okay. Now maybe some techniques. Just the ideas. We make this transformation of variables here. So we introduce the y variable. Then we semi-discretize the equation in time, given by this Euler scheme, in such a way that we only need to solve elliptic equations. Why we are doing this? This just has a technical reason. When we are using this transformation of variables, then the y should be bounded. But the problem is when we are working in H2, this gives essentially bounded functions up to 3 space dimensions, but only in space, not in time. We have not enough time regularity. So therefore, we avoid this problem here by solving elliptic problems. This is a degenerate problem, since we have the exponential factor here, and a priori we don't know if the y is bounded. So we are adding something which ensures ellipticity with the delta. So we have two parameter, the delta t and the delta, and we have to pass both to the limit. This we can do when we have enough a priori estimates, and they are in fact all given just by this inequality here. Okay, and then the rest is techniques. We are using fixed point argument and compactness. Okay, so this is how we can get the existence of solutions. And there's another interesting structure, and this comes from gradient flow theory, In fact, from gradient flow from the work of Felix Otto, we know that the heat equation can be written as a gradient flow with respect to the Wasserstein distance, or said in much simpler words, and maybe simplifying words, is when you're taking the logarithmic entropy and the variation of this entropy with respect to n, and you plug it into this expression here, this kind of, if you like, gradient flow structure, then you get the heat equation. Okay, so this is known. What is also known is when you compute the entropy dissipation, so just the negative derivative of the entropy, which I call the Fischer information, this E2. When I differentiate this object here with respect to n, or take the variation, then I get this object. This is the Bohm potential, by the way. If I plug it into this expression, then I get the fourth order model. Now I could proceed. I can use the entropy dissipation, which comes out from taking the time derivative of the Fischer information. So this object here, I call this E3, kind of new entropy. So written down again here. And I take the variation with respect to n. I get this object here. I plug it in, and then what I get is a sixth order equation. And in fact, this is the correct equation which you get when you derive this model from the Wigner-BGK equation. Which is done by, again, de Gaulle, Merz, and Ringhofer, where they made a Chapman-Ansgar expansion in the Wigner-BGK model. In fact, what they got is a non-local model. When you make an expansion on the scale Planck constant and retain only the main expression, then you get exactly this equation here. So it seems that there's a gradient flow structure, which, unfortunately, up to now is not completely understood. Hence, you could proceed further and further. Okay, let's just be happy having this equation and trying to understand how to get some analysis results. And the nice feature is that, in fact, also this equation looks very complicated. Sixth order is very rare in physics. There are some equations, so for instance, thin film modeling, but there are not many. This is another example. But still, we can do some analysis using the same techniques as I've explained before. There's almost not much change on your ideas involved. And in fact, what we can prove is, again, when the entropy is bounded up to 3 space dimensions, then we get a weak solution, which is now negative, and having this regularity here in the H3 space. So we'll have space H3, and we have exponential convergence to a constant steady state for some constant kappa here. And the ideas of proof are just like before. We are making an exponential variable transformation to get some non-negativity results. We need an entropy estimate, or what I'm calling entropy estimate. So we take the time derivative of this E1, and you need to prove that you have this dissipation term here for the third order expressions and the sixth order, or the sixth root. In fact, this you can again prove by the systematic integration by parts formula. It's quite complicated, but you can do so. And then the remaining proof is just like before. You add some regularization, you make a time discretization using compactness methods, and so on. So the same like before. It's not completely true, since there's a technical detail, and the technical detail comes from the fact, I will go back, comes from the fact that we are not proving the existence of solutions in that formulation, since here we have the logarithm, which is not so nice. In fact, here you see from this estimate that it seems better to write the equation in terms of square roots. And in fact, this is what we're really doing. So we need somehow the existence of solutions of that object here. It looks complicated, but it's just long. And in fact, what we need to do is that we pass to the limit delta going to 0 here in this regularization factor. There's a problem. And the problem is that we have here the fourth root. And we have no information about the fourth root. So we have an information about the square root, which converges weakly in H3 and strongly in L2. So I'm here neglecting somehow the time derivative. You can think of a discrete time derivative if you like. We also know that the sixth root is bounded, but we want to have some strong convergence of the fourth root. In fact, even with a gradient in front, in order to handle these terms here, which are written in red. And the nice thing is that there's a result which in fact comes from the book of Ambrosio and Savary. It's a consequence somehow. We have been able to prove, and this is joined with Pina Milicic, which is also here in the audience, that when you have information about convergence of the square root and the boundedness of the sixth root, then there's a kind of intermediate result. Then you get some information about the fourth root. And thanks to the many gradients and derivatives information, you get it even for the gradient in L4. Okay, so this you can get. This is a technical detail. Okay, let's come to the quantum Navier-Stokes model. And there, again, you can derive this model from Wigner BGK model. This is done by Brüll and Mihatz last year, doing a Chapman-Ansgar expansion. Essentially the same like what you're doing by deriving the Navier-Stokes equations in the classical context. So you just do it in the quantum context. In fact, I'm also needing here some assumptions, since when you're doing so, then you will get a non-local model, which is clear since quantum mechanics somehow is non-local, by an expansion on the scale Planck constant. And I'm also assuming that I'm in a case where I have almost no rotation, so nearly a rotational case. And then what I get is are these two types of equations in the isothermal case. You could also get something using plugging in the energy equation, the conservation of mass, the balance equation for the momentum, where u here is the velocity. You have the convection. I allow here for a pressure term, which is just given by an adiabatic law. I have the quantum correction, which is of third order, which is even worse than fourth or sixth order, since you don't have a parabolic structure. And the interesting thing is here, the right-hand side, the viscosity. It's typically in the Navier-Stokes context, you have a viscosity which is constant. Here it's not constant, it depends on the density. In fact, it's proportional to the particle density, involving the d of u, which is just the symmetric velocity gradient. Okay, so this model has some relations to well-known models. Clearly, when the right-hand side and the epsilon is equal to 0, then you get the Euler equation of gas dynamics. If just the epsilon is equal to 0, then you get density, Navier-Stokes model with density-depending velocity. And when the right-hand side is 0, then you get the quantum hydrodynamic equations or Madelung equations, which are used also in for Bose-Einstein condensates. I think Weitzu did quite some numerical work on that. Okay, so here not numerics but analysis. Can we understand this equation? And yeah, what are the difficulties? So there are two difficulties. First of all, again, positivity of particle density. How to get it? For third order equations, there are no maximum principle, not clear at all. The second difficulty is that you have an energy for the problem, since it's a Navier-Stokes problem, and the energy consists of the kinetic energy, a kind of your thermodynamic energy, if you like. So the h of n here depends on the pressure exponent, and you have a quantum energy part here, and to the corresponding energy you have an energy dissipation, which is just given by the dissipation. So it makes totally sense, but it's not enough. It's not enough since you only have a gradient for the square root of n, but you have third order derivatives, and you can see that it's quite hard to get some existence of solutions only with that information. Yeah, so you would like to have some H2 estimates, some information on the second derivative. Okay, so this is not clear at all how to get more a priori estimates, but you can do so, and this is interesting. I will give you some hints in a minute. I just define a new velocity variable. So I take the old velocity plus the viscosity times the gradient of the logarithm. And then when I'm doing so, I call this just a new velocity, plugging that into the system. And what I get is a new entropy estimate, or energy estimate if you like, where you have another kinetic energy here. You again have the thermodynamic and quantum energy. And the new feature is now that the energy or entropy dissipation now has an additional term, which is that one, which contains second order derivatives. This is what I want to have. In fact, there's some condition. You have to take into account the epsilon should be larger than the nu. That means somehow the quantum effects should be stronger than the viscosity effects. Okay, then you get an estimate, and this is nice. And the question is there something behind? And this is not completely understood, but there is something behind. For instance, when you're writing the Navier-Stokes system in the W variable, in the new velocity variable formulation, what you get is that is equivalent to this problem here, which I'm calling viscous quantum hydrodynamic equations. So you have, again, this mass conservation, but on the right-hand side you have a dissipation. You have this balance equation for the new momentum variable, involving the pressure and the quantum term, and on the right-hand side you have some viscosity. Here, this exponent, this is coefficient here, is just the difference between the Planck constant and the viscosity squared. Okay, so this model, interestingly, you can also derive it from a quantum model, not from the Wigner-BGK, but from the Wigner-Fokker-Planck model. The Wigner-Fokker-Planck model is interesting since it's quantum mechanically correct in the sense that you can prove that it preserves the positivity of solutions. So we can see that this is this equivalence, and so even just as a coincidence, if the epsilon is equal to 0, then the quantum term just disappears. What you get is a viscous Euler system. There are no quantum effects, at least not visible, but they're hidden somehow in the definition of the W. Okay. Moreover, this velocity here, which I've defined, this you can find it in the literature. And in fact, it has been used in Korteweg type models, viscous Korteweg models by Bresch and Desjardins. There are also third order models, but the third order term somehow is slightly simpler. And using this velocity, they also could get a second a priori estimate beside of that one which you get from physics. Moreover, Peter Markovich found it. In the mixed state quantum hydrodynamics equation, you have called this the osmotic velocity. And in fact, this term goes back to the works of Nelson in the 60s, where he also has defined the second object here as the osmotic velocity. So there seems to be something even more behind that, which is also still not completely understood. Okay, but the nice thing is that now we just have to prove the existence of solutions of this problem. And the good thing is that we have the Laplacian here on the right-hand side. So we have a kind of regularization, which is completely natural, not artificially added. And then what I can prove is the existence of solutions, of weak solutions with these kind of regularity. In fact, there's some condition, and the condition is that the pressure function has to be an exponent which is larger than 3. Yeah. So you know that in Navier-Stokes models the exponent can be not arbitrary, so you need some conditions, but this is a bit too big compared to the classical Navier-Stokes problem. And the reason for that is that the energy estimates give me some information on the square root of the density. The square root of the density in fact in H1 uniformly in time, and then up to 3 space dimensions the square root is in L6. So the density is in L3, but this is not enough to pass through the limit in the approximate problem. So I need a slightly more, L3 plus delta. And in fact, this is exactly the gamma which is here. Yeah, so it's just, for the moment, a technical assumption. Okay, moreover, the weak formulation is slightly more weaker than what you would have. I need test functions which are multiplied by n squared in order to avoid that the density may touch 0. This may also happen. Okay, let me also mention that the estimate I've shown to you has been derived only where the Planck constant is larger than the viscosity. In fact, Chinese groups have improved this result by allowing for any kind of epsilon, large or small, by combining the estimates which are available and proving something new. Okay, then in proving this theorem here for the viscous model, is then somehow not so difficult, at least when it took me some years to understand it, but then in fact it's not so difficult since the mass equation is just a parabolic equation, so you can apply a maximum principle. It's very nice. There's a drawback, and the drawback is that the velocity should be smooth. But the velocity is not smooth since the viscosity depends on the density, so you don't have a Laplacian of the viscosity somewhere. And so you have problems to do so. Therefore, I'm using the Fayet-Galerkin method, so like in the works of Farese for the classical Navier-Stokes model, which gives me a smooth W. Then I can apply the maximum principle, everything is fine, and then I need to pass to the limit. And passing to the limit is just done by using these estimates, which I already have before. Okay, so let me summarize what I've presented to you. So I've presented essentially three class of models, and some results are solved, some problems are solved, some are not solved. So for the fourth order model, we have global existence in the 3D case, we have long-time asymptotics, we do not have in general positive solutions, they may touch zero. For the sixth order equation, we also have existence in long-time asymptotics. We do not know if positivity is preserved or not. For the quantum Navier-Stokes model, the same. And then I've shortly mentioned the full quantum Navier-Stokes model, where you include the energy equation for the moments. There's nothing known for that. And yeah, for this talk, the only thing what you might want to remember is two things, two new ideas to derive a priori estimates. The first one is the systematic integration by parts, which helps you deriving a priori estimates. And the second one, it's this osmotic velocity variable, which seems to appear in different contexts in fluid dynamics. Thank you for your attention.
What is the problem, or why do you avoid vacuum? So it could be, right?
Yes.
I
Could
know
be.
that there's a lot of problems in the technique, but you cannot say that it's not real, and it could be.
Right. I mean, I'm not avoiding in the sense that I'm looking for positive solutions only.
Yeah.
I have non-negative solutions, but I have problems in the weak formulation.
Yeah, I know.
So how do you find the notion of solution?
There are not
Yeah.
lots of solutions where you can have.
Maybe yes. I mean, analytically, so numerically, I think we never have problems with the positivity, I think. But in fact, for certain ranges of parameters, the numerical solution breaks down. So you don't know really what happens, especially for these quantum hydrodynamic things. There are some difficulties.
There may be a vacuum.
For the quantum hydrodynamic model without any viscosity, that let's say the conjecture that you might have vacuum, and then just the equivalence between Schrödinger and Madelung breaks down, and you don't know what to do. For these kind of models, I don't know. It's open, completely open.
So if away a vacuum, this model can derive from the Schrödinger equation by the Madelung transform. If there is a vacuum, is there other way to derive this model?
You mean the quantum Navier-Stokes? The quantum Navier-Stokes, I think, is not equivalent to or cannot be derived from Schrödinger.
So not with nu equals 0.
Okay. Yes. In fact, from the, let's say, mixed state Schrödinger system, since I have here the pressure term. When you also neglect the pressure term, then this is formally equivalent to the Schrödinger equation.
Away vacuum, right?
Away from vacuum, I think Peter did something with Ingo to give also some definition when you have vacuum.
Yeah, but the closure condition.
I mean without pressure, single state, only single state.
Well, no. If you have multiple states, basically what Ingo showed was that you get essentially what you get is the divergence of a positive definite tensor, but you don't know what it is. It depends on all the states. So the closure condition is the condition. So this is modeling. The P of n.
So in fact, it's a critical point what you're mentioning, since these Madelung equations, so without this term and this term, it's not clear if the model really makes sense when n touches 0.
You can get these equations by taking the first two moments of the Wigner equation for the single state case. So that's fully.
Yeah.
Right, Ingo?
If you know, if you're in a single state and you know that there's a Schrödinger equation behind,
Then the
Madelung equations hold in a rigorous way. Vacuum or non-vacuum. That we can prove. But,
common, if a reasonable just do some simulation to compare how the vacuum motion from the outer system, Schrödinger system, and this non-stable system. Well, nothing don't do it yet. But outer system, the vacuum move parallel, never merge. But from Schrödinger, fixed epsilon, they merge. And when epsilon becomes smaller, smaller, the merge time becomes longer.
Yep.
Where is this Laplace n from?
This one here?
Except that you enjoy having it. But
This is just the transformation. The W is the
Okay,
of the logarithm.
sorry.
So it cancels just out. It's yeah. So, which also numerically is nice.
Right.
But I should mention that numerically it's quite difficult since the problem is that you have a competition between quantum effects and dissipation. And at least what we observed is that even for very small dissipation, the quantum effects can be destroyed very easily, which is somehow clear since quantum effects are something related to coherence, and dissipation is decoherence. But it is, let's say, one potential approach to include dissipation into the system without completely destroying quantum effects.
How restricted is this inequality gamma bigger than
for the moment, there's a restriction in the sense that we are working in this H2 space, and we want to have here L infinity in order to define this transformation of variables, this exponential transformation of variables.
and physically?
Physically. No. Physically, we are happy with a three-dimensional case, since this is, let's say, the interesting physical dimension. I guess that you can prove it also for higher space dimensions. So for the quantum Navier-Stokes, I don't know, but for the fourth order model, this has been done by Savary and Toscani. They have the approach more coming from Wasserstein distance or mass transportation theory, and they can allow for any space dimension, as far as I know. So here it's, let's say, a technical thing.
Okay, yeah.
One more question. So in the fourth order case, you use this transformation n equal e to the y, and in the sixth order case, you didn't do that, right?
Yes.
So could you?
Also in the sixth order case, we're doing so. Yeah, the reason is, okay, then I have to go again to the sixth order model, is that again here we have a symmetric structure.
Yeah.
So this is nice for defining bilinear forms in Lax-Milgram. We have a perturbation here, but which is of lower order. And we are essentially using different kind of formulations of the same equation. So this is nice for proving the existence of the approximate problem, but it's not nice for passing to the limit. For passing to the limit, we need this a bit more lengthy form.
And it's not nice for vacuum.
Let's say this. I mean, this. Yeah. If you like, so it's not nice for vacuum.
Y goes to infinity. N goes to 0. Y goes to infinity. Right?
You mean for the transformation of variables? Yes, right. We would lose the bounds on y. Right, and then it's difficult to define the equation. Yeah. This is the reason why we are working with this problem only. Yeah.
So then, let's thank all the speakers of the morning.
Thank you.